Today I would like to speak a few to give you some introduction, a few aspects of electrodynamics in conducting moving media and general aspects of the dynamo problem. These are the basic equations for all I would like to speak about. Our basic equations are Maxwell equations in some approximation and constitutive equations like Ohm's law. Generally speaking, I assume that I'm in a flat space-time, no general relativistic effects, otherwise these equations would look a bit different. And I use magnetohydrodynamic approximation. That means mainly sufficiently high electric conductivity and non-relativistic velocities. That means velocity over velocity of light, or all terms in the square of this quantity are neglected. So, Faraday's law is used in general form. In Ampere's law, it belongs to the magnetohydrodynamic approximation that the displacement current is neglected. And divergence B is equal to 0. Ohm's law looks in general a bit more complicated. In general means without the restriction to small velocities. Firstly, you have in addition the convection current, electrical charge density times U. And this is of the order V over C squared compared with J, and so it is neglected. In general, you have not a simple conductivity, but you have two different conductivities depending on the velocity, two different velocities, one for the component of J parallel to the velocity and the other for the component orthogonal to the velocity. But in the MHD approximation we have simply this. I exerted here a term E external. It stands for, say, a battery. If you have a known electromagnetic force which moves charged particles, then you describe it by E external. So, for example, if you have a gradient in the chemical composition of the medium, or if you have thermoelectric effects, also all this is described by this term, which I will often neglect. The fact that you have no convection current is closely connected with the fact that I don't have the third Maxwell equation, divergence of D, displacement, equal to the electric charge density. I need the charge density not here. It doesn't mean that this force Maxwell equation doesn't apply. It applies, of course, but we need it not for our derivation. I always assume that the magnetic permeability is magnetic permeability of free space, and so constant. Okay. I should mention that the magnetohydrodynamic approximation also implies transformation properties for the electromagnetic quantities. fields like E or B or the current density are even in the special relativity components of 4 times 4 tensors or a 4 vector. And they follow the transformation laws for these quantities. In MHD, the situation is very simple. The quantities like B transform like, say, the force also, they follow Galilean laws. So also H and J, only B follows a law like this. This is the only deviation from Galilean transformation, and this is also the reason why you have this term in Ohm's law. If you start from J equal to sigma E in a system in which you have no motion, then you come to this Ohm's law in a moving, or if you have a non-zero velocity. Okay, you can solve the first two Maxwell equations. Usually they are called the homogeneous Maxwell equations by potentials. B is solenoidal, that means you can represent it by a curl of a vector potential. And if you put this here, then you have curl of E plus d over dt of A is the curl of that is equal to 0. That means it is a gradient, and this is just written here. This is completely equivalent to the Maxwell, these two Maxwell equations. You can derive these two Maxwell equations from this. This implies divergence B equal to 0. And if you take the curl of this vanishes and you get just Faraday's law. You know that A and phi are not uniquely defined. You have gauge possibilities. A, B and A are invariant under these transformations. And this psi you can fix A and A, for example, by saying that A should be divergence free, or you can also choose the Lorentz convention in this form, or you can use other gauge possibilities. Okay. So, we have spoken about the two homogeneous Maxwell equations. Now, the only inhomogeneous we have is curl of H equal to J, or if I can write it in this way. And if I take a vector potential A, which is divergence free, I have this equation for A, that means a vectorial Poisson equation. And you can solve it assuming that the current behaves properly at infinity, and you can write the solution of this equation in this form. And if you take the curl of this, then you arrive just at Biot-Savant's law, which allows you to calculate B from the current distribution in this way. Sorry, I fear it will happen again each 10 minutes.
We need to connect one more time.
So we have to.
Shouldn't be strange.
Okay. Yeah, this integral in Biot-Savart's law has a remarkable property which I want to explain to you. It is again the equations you had on the slide before, also this solution of this vectorial Poisson equation, and I make a coordinate transformation so that the x is no longer here, but it is here as the argument of j. If you then take the curl of A, that means B, you have simply the curl of J. And this representation tells you that if you change J by adding or subtracting any gradient, then this integral will not change. This is an interesting aspect which we will use in the following, and perhaps I should tell you a story originating by my teacher Max Steenbeck. He was in the Second World War involved in the deactivation of sea mines. So sea mines are mines which are underwater, and they have a magnet needle in it, and if a big iron body, a ship, approaches, the Earth's magnetic field is some way deformed, and the needle moves and gives an electrical contact, and it explodes. And he had the duty to deactivate such mines. So one possibility is to take again an iron bolt and to make it a big magnet by adding a coil here and feeding it with current. Then the sufficient change of the magnetic field for making this exploding is already in a larger distance, and it will explode before the boat is there. I think it is not a very pleasant job, to be honest, but it will. The other possibility, and this has something to do with Biot-Savart's law, is take a wooden boat, say the mine is here, take a wooden boat, have a battery connected with a short cable whose known isolated end is here, and another long cable. The known isolated end is here. Then a current flows through the water, through the salt water, something like this. The problem was to estimate the magnetic field caused by this current system. And what these people did was take Biot-Savart's law for this estimate, but inserted only this current and this current, and not this, because this current follows this law, and this is a gradient in the case of in the quasi-static case, and so this current doesn't contribute to the magnetic field. So this is an illustration of Biot-Savart's law. Okay, next story. You know that you can derive the induction equation. Yeah.
This you derive by assuming the Coulomb gauge, right? But it's a gauge invariant statement.
Yeah, but the result for B must be independent of this.
Correct. But on the other hand, when you inverted it, so it must, the same derivation holds in other gauges?
Sorry, say it again in the water.
When you derived the potential, it was in the Coulomb gauge.
Mm-hmm.
We wrote down the expression for the vector potential in the Coulomb gauge.
Yeah,
Or is it
but
divergence?
I think this is story which had nothing to do with this. I derive in a correct way Biot-Savart's law in this form, and then you can forget the derivation. And then it is clear that a change of the electric current by a gradient has no influence on the integral. Does it answer your question?
Yeah, that's okay. It's just a curious thing for me, that's all.
Yeah. Okay. Yeah. Here are again Maxwell's equations and Ohm's law, and you know you can derive from them the induction equation. Start with dB over dt, replace E by Ohm's law, J replaced by by the curl of B, and then you get this equation with eta equal to 1 over mu sigma magnetic diffusivity. It is usually a homogeneous equation, but if you really consider an external electromotive force, then you have an inhomogeneous term. You can define the magnetic Reynolds number. The magnetic Reynolds number is in fact the ratio of the induction term here to the diffusion term here. That means small rm, in the case of small rm, the u plus b term is not very important. In the case of very large rm, it is just important, very important compared to the diffusion term. Okay, have a look on the magnetic energy balance. Again, the equations you need. Magnetic energy density is defined by d squared over 2 mu, and you can derive from these equations, not from so, this relation, the so-called energy integral of the Maxwell's equation. In general, you have on the left-hand side, you have on the left-hand side also the term time derivative of the electric energy, here magnetic constant times a squared over 2, but in magnetohydrodynamics this electric energy is small compared to the magnetic energy, and that's the reason why it doesn't occur here. Okay, S is a pointing vector, and yeah, this form of the energy balance doesn't depend on Ohm's law. I have just J's there and not J replaced by E also. You can investigate the total magnetic energy in all space. Assume you have a finite conducting body, and it is surrounded by free space, and takes the integral of this over the full space. This gives you the left-hand side. On the right-hand side, yeah, you can first consider a big body, and is it better? Thank you. You can you can take the integral over S, and you can convert it into a surface integral, and can draw the surface to infinity, and if S behaves reasonably, then this contribution vanishes. And in the GE you can replace E according to Ohm's law, then you get a term like this. It is the ohmic heat production, which always makes the magnetic energy in all space lower. This is the work done by the Lorentz force against, or done by the Lorentz force. Work done by the Lorentz force. If this integral is positive, the Lorentz force works on the motion, and this reduces the magnetic energy. If it is negative, you add magnetic energy to the system. And at the end, you have again a term like this. It is again known electromagnetic forces which drive currents, and they can, depending on the sign of the integral, make the total energy larger or small. Okay. Consider the induction equation in the limit of small magnetic Reynolds numbers. Consider eta as constant. Then it takes this form. I mention this mainly because of a mathematical aspect. You can solve a mathematical aspect which we utilize later also. You can write down the solution of this equation in infinite space in this way with a Green's function. Each Cartesian component of this equation is a heat conduction equation. I have written it on another slide. This is a heat conduction equation. And you can write down, I replace the coefficient here, or I call the coefficient here also eta. There's a connection with what I want to tell you. You can write, thank you. So, do you hear me better now? You can solve this equation in this way. You see easily that it is a solution. You have to show that it is a solution, and that it gives you the initial value. So first, it is a solution. Consider the operator eta Laplace minus the d over dt. You can just draw it through this integral. Then you have here the expression which is equal to 0. If you draw it through this integral, we have first the same here, but the time differentiation acts only on this integral with the upper bound t. And you know, if you differentiate an integral with the upper bound t, then you have the integrand with integration variable replaced by t. So you get this with 0 here, but the Green's function has a property that it goes to the delta, three-dimensional delta function. So you just produce the right-hand side. So you have a solution of this equation. This equation satisfies the initial condition. If you have t equal to t0, this doesn't contribute. And here you have again a 0 in the Green's function. And the result is just t at x and t0. So, and this you can use in the induction equation, each component of the induction equation, and you find just this solution. We will use it later Okay. Next point, magnetic flux. You can define the magnetic flux through a surface S in this way. Take B and a scalar product with vectorial surface element, with a vectorial surface element ds. This is the magnetic flux. This magnetic flux can change in time by two reasons. First, because B changes, and second, and if you assume that the surface moves with the fluid, it can change because of this motion. You can derive first this relation dphi over dt is equal to this integral. This is a time variation of B, and this is the effect of motion. This has uses only divergence B. It has otherwise nothing to do with specific properties of the magnetic field. I have written it on the next slide. Consider any vector field F and a moving surface moving with a velocity phi, then you can derive a simple geometrical consideration this relation for the time derivative of the flux. In the case of the magnetic field, this term vanishes with B, and you get this relation again, which has nothing to do with Maxwell's equation or equations governing B, except divergence B equal to 0. Now use Maxwell's equations and replace the B over dt by minus curl of A. Then you get just this relation, and you can use Stokes' theorem and can transform it into integral over the rim of this surface S, ds. This is a vectorial differential of along the rim. And if you use Ohm's law in this form, you see that the flux, the time derivative of the magnetic flux through the surface is just an integral over the rim of this surface minus J over sigma times dl. Okay. We are interested in particular in next one. In the induction equation in the high conductivity limit, that means sigma or magnetic Reynolds number tends to infinity, and again we put for convenience only the external electromotive force equal to 0. Then the induction equation turns into this simple equation, and this is equivalent with the phi m over dt equal to 0 for any material surface. That means it is equivalent. You can also take this relation, this statement, and you can derive this equation, the induction equation for Rm tending to infinity from this. And this leads to the concept of frozen-in magnetic flux or frozen-in magnetic field lines. Take a surface in an infinitely conducting fluid and consider the magnetic field lines which cross the surface, or the total flux represented by these field lines, and this flux or with the usual appointments, the number of field lines through the surface doesn't change. Okay, I think you know this concept, and I need not to explain more, but I will explain one consequence which is of interest for dynamos. It is a theorem by Bondi and Gould, which already originates from 1950. Consider again a finite fluid body in free space. Assume, to be mathematically correct, that V and V dash are simply connected, not a ring of a conductor or something like this. Then outside, it should be V dash outer space. You have B equal to a gradient, curl B equal to 0, and if you have a simply connected space, it is equivalent to B equal to gradient phi, with phi satisfying the Poisson, the Laplace equation. Homogeneous Poisson, that means the Laplace equations. Then you can represent phi in this way. These are some constants, and this radius in the power n plus 1, and these are spherical harmonics, depending on theta and phi, spherical coordinates theta and phi. Take a one term with n equal 1, then you have this, yeah, it is a 1. This y 1 m are just cosine theta, sine theta, cosine phi, sine theta, sine phi, and you can represent this in this way. This is only a convention to take the mu and the 4p here, and otherwise it is a scalar product of a quantity m with the radius vector r divided by r to the power 3, and you can simply show that this m is given by this relation, half integral over r cross j, and it is a magnetic dipole moment. You can do the same with the other terms, and you have then a quadrupole moment, which is a second rank tensor, and higher moments. In the case of an ideally conducting fluid, Bondi and Gould have shown that this m is bounded. And later I generalized it in the sense that all C and M, also higher magnetic moments, are bounded. The idea is, take a surface, consider a surface at the surface of this body here. Then the flow which goes out, also the number of field lines, don't change in time. You can move this piece of this surface and can rearrange, say, the foot points of the magnetic field outside, but you cannot produce an arbitrarily strong magnetic field outside. So whatever you do, you can amplify the magnetic field in outer space only to a certain level. It cannot grow endlessly. It is an interesting aspect in dynamo theory. Okay. Yeah, let me say a few words about the representation of the magnetic field by colloidal and toroidal parts. It is a useful representation of the magnetic fields in spherical and related problems. Consider a spherical coordinate system and consider first an axisymmetric, otherwise arbitrary field F, represented in this way by the three components, and in a properly chosen coordinate system, the Fr, F theta, and F phi doesn't depend on phi. Then you can split F into a colloidal and a toroidal part, and can define these parts just in this way. The colloidal part lies completely in meridional planes, has no phi component, and the toroidal part is completely perpendicular to it. That means has only a phi component. These parts have a lot of very interesting properties. So, for example, the curl of F colloidal is always toroidal, and the curl of F toroidal is always colloidal. You can simply calculate the curl of this, and you see it has only a phi component, no other components. That means it is toroidal. You can take the curl of this, and you see that it has only R and theta components. So there are other interesting properties. So, for example, the divergence of F toroidal is always equal to 0. The divergence differentiates the phi component to phi, and it is 0. Okay, this is only the axisymmetric case. Consider. This. Yeah. Consider now an arbitrary vector field. You can represent each vector field in this way: 3 terms corresponding to 3 components. Consider first, in order to see that this relation is justified, consider first the magnetic field on a given surface R equal to constant. So it means that's the vector field on a given surface R equal to constant. And you can represent this two-dimensional, this vector field in 2 dimensions by a curl-free field, a gradient field, and a divergence-free field. In 2 dimensions, the divergence-free field can be always represented in this way. It is a field which completely lies in this plane R equal to constant. If you focus attention on surface R equal constants, you have only a gradient with the 2 components, with the theta and phi components. If you now admit, or you go again to the full space, this gradient has also R component, which is then defined by VW, and which need not to coincide with the given R component of F, but you can always correct it by adding a term R times V. So this is indeed a completely general representation of a vector field, of a vector field. You can put again F equal to a colloidal field and a toroidal field. And you can define or redefine the colloidal field in this way and in this way, just by requiring that it can be represented in this form. This is a unique definition. Why it is a unique definition? You have to study the gauge possibilities here You can, of course, add, I could do it here. You can see it here. You can transform u in u plus a function of r. It doesn't change this term r cos gradient u. You can change w in this way. Then you change the gradient. You give him an additional r component. You can compensate it by saying that v is v minus 1 over r dt over dr. And you can show that it is the only possibility of gauging this scalars. And this gauge doesn't change this term. It changes these individual terms with v and w, but not the sum. And so, indeed, requiring that f poloidal should look like this and toroidal look like this is a unique definition of poloidal and toroidal fields. Again, the toroidal field has no r component. It has now a theta component in contrast with the axisymmetric field, which vanishes if you say that there is no phi dependence, but it has no r component. F poloidal has r components. What is interesting is that you have again such relations, that the curl of Fp is toroidal and the curl of Ft is poloidal. Just calculate this curl and you will see that this curl can be written in this form. And calculate
Yeah, it works.
I
It's
see
okay.
it on the screen.
It's okay now.
Calculate this, and you see it has just the defining property of a poloidal field. It can be written in the form R cross gradient of some scale. So you have again divergence of f toroidal equal to 0. F toroidal has this form. It is just minus curl of r times u. And this is a curl, and so it is divergence free. Okay, and we apply this now to the magnetic field, which is divergence free. Well, we write again, magnetic field is a sum of a poloidal and a toroidal field. And yeah, look first of the toroidal field. I have just chosen a form which defines a toroidal field. I have only, by reasons of tradition, called the scalar T. Should remind of toroidal. The poloidal field can be, this is divergence free. By this reason also the poloidal field must be divergence free. I can write it as a curl of something. Something means it must be toroidal in order to have a poloidal BP. And so I choose here the general form of a toroidal field. So this is a general representation of P. Here it is a bit more explicitly, again, toroidal field, yeah, it's nothing new. No R component, the toroidal field is completely in surfaces R equal constant. And the polarized field is intrinsically three-dimensional. The quantity omega, or the operator omega, which I have written here, is just the angle part of the Laplacian. This is defined here. You know that you can write the Laplacian of S in the form 1 over R d over dr R square d S over dr plus 1 over R square omega S, and my omega is just in this sense the angular part of the Laplacian. Only one consequence: consider again a conducting body and free space outside. Consider the free space, then you have there curl B equal to 0. You can say B must be a gradient, but a toroidal field cannot be a gradient. This doesn't correspond to the definition of. So the toroidal field must be 0, and the poloidal field must be just this gradient. Okay. Another more mathematical aspect, symmetry properties of the basic equations. I mean, these equations. These equations have the following have certain properties with respect to changes of the quantities E, B, J, and so on. We define a translation of these fields. So it's just defined in this way. We shift it along an axis. We can define a time shift, and we shift it along the time axis. We define a rotation where we take the object and turn it around any axis. This way I define the field F rotation from the field F. You can do it a bit more mathematically. D is a matrix which describes orthogonal coordinate transformation. Such a transformation, and we consider first a transformation with a positive determinant of dij. This is just a rotation. So we define a rotation in this way, and we can also define a reflection in this way with a matrix D, the determinant of which is -1. So the simplest example is dij equal to minus Kronecker ij. So these are ways of generate new fields from a given field. FDR, FDS, F rod, F reflected from the field F. And now the Maxwell equations have the following property. If they are satisfied with a set E, B, H, J, U, then they are also satisfied with translated fields. They are also satisfied with the time-shifted fields. They are also satisfied, which is more remarkable, with the rotated fields. They are satisfied with the reflected fields if you, in addition, put a minus sign in front of B and H. It is a simple exercise to show this these properties. We will use it later. Okay, I have spoken here only about changes of the fields, E, B, and so on. I have not spoken about coordinate transformations. But this statement I make here is closely connected with the behavior of the Maxwell equations under changing of the coordinate system. As long as you think about vectors, not pseudovectors, vectors, and define their transformation properties so that these are the same transformation rules as for the coordinate differential. You know in which way this quantity changes if you go to another coordinate system, and if you take, you can define vector fields by this transformation property of dx1. If you do this, the Maxwell or the component representation of the Maxwell equations changes under coordinate transformations. It changes just in the case when you go to a coordinate system with a determinant d equal to -1. Then there are sign changes in the component representation of the Maxwell equations. You can say, okay, I can live with this. This same sign.
Touch again. Should be persuaded.
Yeah. These sign changes don't reflect physically relevant symmetry break. The reason is simply the mathematical formulation with curl you have chosen. You should be aware that you can define the curl operation in a coordinate independent way on the basis of Stokes' law, Stokes' relation. And so, curl F multiplied with a surface element integrated over a surface is, according to Stokes, integral over the edge of the surface, F d, let me write, L is the differential along the curve which gives the edge of this. But this applies in the, in the case if you have assigned the circulation here by a right-hand rule to this differential S. Otherwise you have to take a negative sign. And you can, that means you have introduced a right-hand rule. You can now consider this for a small element, say for, so take a surface which corresponds to x equal to constant in the y and z plane, and consider, for example, then the x component multiplied by the surface. Oh, it's bad that I denote the surface also with f, but this is the surface of a surface S times this integral ds f dl. If you go to the limit of a small surface f, then you can use this as a coordinate invariant definition of the curve. But you must be aware you have used a right-hand rule for this definition. And you can understand the Maxwell equations, or the curves in the Maxwell equations, as defined in this way. So you have introduced by your mathematical representation a right-hand law and not a left-hand law. And so no wonder that you have this property here on the reflection. The reflection would invert a right-handed structure into a left-handed structure. So that's a comment on what I said. This signs there don't indicate a physically relevant symmetry break. It is you have produced it by using a mathematical operation curve which you have defined it this way. You have introduced it with this. Okay. Yeah. What? And I already said you can write down the component form of the Maxwell equations and can study how this form behaves under these transformations. And then you get again a minus sign at several places if you consider a transformation with a negative determinant, by just the same reason. You can say, okay, I can live with this. I know that if I reflect fields, I have to add this. I have to add these signs. There are people who say, no, I don't want to live with this. I introduced two kinds of vectors, polar vectors and axial vectors, with different transformation laws. If I change the coordinate system, then you have, then you maintain or you produce the fact that the form of the Maxwell equations doesn't change under any coordinate transformations. But you have only shifted the problem to another place. Okay, so far about polar and axial vectors, and you can extend it to scalars, real scalars and pseudo-scalars and tensors, and so on. We will use the concept I have written down here, at least at several places. Later we will also change to the concept of toroidal and toroidal fields. Okay. Now a few words about the dynamo problem. Consider again a conducting body, simply connected, no ring or so, and surrounded by free space. Then the Maxwell equations must be satisfied everywhere, of course. They apply everywhere. Inside this conducting body, you have Ohm's law in this form. Okay, take this. Ohm's law in this form. I don't consider here an external electromotive force. Outside, the current is equal to zero. You have also your magnetic field. If the causes of this magnetic field are only inside the fluid body, must decay like a dipole field if you go to infinity, you must have this. These are basic equations for the dynamo problem. You can write them in another way. Inside the fluid body, you can derive the induction equation. Outside, the curl of B and the divergence B must be equal to 0. That means B must be a gradient in outer space. You can derive from the Maxwell equations that there is no jump of the components of B at the surface. That means, no, I must admit, I make here the assumption that there are no surface currents in the sense of a singularity of the current density J at the surface. If I exclude such singularities, then I have the continuity of B at the surface. These brackets mean the jump equal to 0, and again this condition. We speak in this case of a dynamo if these equations, or the equations on the slide before, allow solutions which don't tend to 0 if time goes to infinity. This is our understanding of a dynamo. I see I didn't make some completions. Okay, I want to say at the end, we know some constraints for dynamos. Dynamos are independent of the magnetic Reynolds number, which describes the intensity of the fluid flow. Dynamos are impossible under certain conditions. The first anti-dynamo theorem was, in a simple form, proved by Cowling already in 1934. Later, there were many investigations. Cowling considered the case, the static case, and assumed that both the fluid velocity and the magnetic field are axisymmetric, and he showed that there no magnetic field, no dynamo, no maintenance of the magnetic field is possible. Baginski extended this to the non-static case, but he assumed that the fluid flow is divergence-free, and there are more things. In between, it is clear that for a very wide range of assumptions, we can say there is no dynamo with a magnetic field which is symmetric with respect to any axis. That means, if you consider the Earth or so, we don't speak about the symmetry of the magnetic field with respect to the rotation axis. Or so. As soon as you can find any axis with respect to which the field is axisymmetric, you can exclude a dynamo. There's a planar version of this theorem. There is no magnetic field which depends on two coordinates, two Cartesian coordinates, only in a fluid of infinite extent in the direction of the third one. It means you cannot have a field in which dx, dy, dz depend only on, for example, x and y. You must have an additional z dependence if you want to have a dynamo. Okay. These were conditions for the magnetic fields. And is a group of conditions for the fluid flow. There is no dynamo due to a known radial flow in a spherical body under certain conditions for the magnetic diffusivity. So consider you have a flow in a spherical body only in surfaces are equal to constants, no radial components, then this flow cannot make a dynamo. This theorem traces back to Alsace. I forgot to correct it here. To Alsace, and it was it appears again in Bullard and Gelman in 1964, and later I think it was I was in Jones proven in a more general way, not assuming solenoidal flow. There's again a planar flow, or planar version of this theorem. A planar flow in an infinitely extended volume, and a planar flow cannot produce a magnetic field. And with a planar flow, I mean U is, for example, Ux, Uy, and no third component. There are the more detailed conditions concerning the magnetic diffusivity. And a last remark, you know that dynamo models exist. Not all can be excluded by the theorems I mentioned. And in all dynamo models, the dynamo consists in an interplay between poloidal and toroidal fields. This is a general observation. And you may ask, is it possible to have a dynamo in which you have only a poloidal field or only a toroidal field? It was a long time an open question in Kaiser in 1994 and 1995. Proved under very general conditions that you cannot have a spherical dynamo with a purely poloidal field or a purely toroidal field. Okay, there are a few more such theorems, but I think I have shown you the most important ones, and I have reached just the end time. And let me stop here. These were the aspects of electrodynamics of moving fluids, moving conducting fluids, which I wanted to explain to you and which I will use in our considerations about mean magnetic fields. See you tomorrow.
Thank you, Carl.
Thank you.
Questions? Part here in the connections. Question, please. I mean, yes, please.
You talk about kinematic dynamo problem.
Yeah.
What really means kinematic? Is an approximation of the model? Or?
No. The approximations are the approximations I mentioned in the context of the basic equations, and I mean that the velocity is given. The velocity of the fluid is given, and we don't consider constraints which come from the Navier-Stokes equations also. So it is more general. You can specify it in the sense that U is governed by the momentum balance by the Navier-Stokes equation.
Okay. So it's not concerned to B goes to 0 for T that goes to infinity.
No, I did not.
So at some point you introduce the approximation that B, the magnetic field, goes to 0 or the time that goes to infinity.
No, I defined the dynamo by the requirement that it should maintain the magnetic field over arbitrary times.
Okay, so
In that sense, I said it should not go to zero if times goes to infinity.
so that is the definition
Yeah.
of dynamo.
Of course, I have cases where I have slowly decaying fields. We don't consider this situation as a dynamo.
Okay, thank you.
In the astrophysical context, by dynamo one always means self-excited dynamo. That's another convention. The dynamos are sometimes also used when they are non-self-excited, for example in technical devices. But in astrophysics we talk typically about self-excited dynamo, so that's an adjective that is not always made.
But it is implicitly contained here. I have no force like E external also. And if I have a magnetic field, it comes from the initial conditions, but not from, yeah, it is self-excited.
So I can,
Is it a reasonable assumption that there are no surface currents on the boundary of the dynamo region?
Yeah.
Is it reasonable, and why is it there are no surface currents?
I have no good answer, but it is reasonable. If you would have, for example, a surface charge, then by the rotation of this body, a surface current would occur. But in in magnetohydrodynamics, these surface charges are very small, and this surface current would be of the order of V over C squared compared to this J. I'm aware that it is not maybe not a completely satisfying answer to you. Perhaps I have an idea about your question, how exactly exclude surface currents.
Any other questions? Yes, please.
When you mentioned the Bond-Gold theorem,
Yeah.
you had a phi and a phi dash. Is it something like, so do you have phi and phi dash, which are simply connected on two sets of spins?
The Bond-Gold theorem is proved for a simply connected body surrounded by free space. And then also the free space is simply connected.
So some region in the space outside of this volume.
Yeah, I thought here of all the remainder of the infinite space, this free space. Fluid body in the infinite world. Then I wrote down the potential with powers of R, so this potential ranges until infinity. I don't know whether I really catch it.
Maybe you should try to clarify
I
why.
was mainly thinking because if you have phi, so if you have some simply connected region phi, and all the rest of it is phi dash, then the phi dash isn't simply connected.
V dash is?
It's not simply connected.
Why not?
Because if
You define the simple connection by saying you must be able to contract a curve to zero without going through a region which doesn't belong to this
so then if
space.
I take
And if you have a body here and all other is V dash, all space about, you can take any curve here and contract it to a point without going through this.
yeah, I was thinking in 2 dimensions.
No,
Yeah.
3-dimensional. Yeah.
I mean, that is, but it is topologically different from not having, from completely filled thing.
Sorry, I didn't.
If you take curves, you will do this, but if you put spheres and try to contract, you
Yeah.
get something, you'll not be able to do that. And so it is different from something which has no holes. That's all I think he's trying to say.
But maybe you should try to clarify why fast dynamos can work at all then. I mean, it sounds like fast dynamos have generally a problem, but that's, which means in the limit of infinite conductivity, any dynamo in a sphere.
I think if you have infinite conductivity, the dynamo problem is not a, how to say, a well-posed problem. You have no decay of magnetic
You first the order of two limiting transitions, right? Time goes to infinity and eta goes to zero. It's important in what order you take two limiting transitions. First, you take t equal to infinity and then equal to zero, not the other way around. So you always look into non-ideal MHD. You always solve non-ideal MHD.
No, but you are,
until the last movement.
But that sounds like you are saying the growth rate really goes to zero as the conductivity goes up.
I think so.
Zeldovich thing. The Zeldovich, for a Weinstein-Zeldovich example, where we stretch Western pole.
It's Zeldovich.
Oh, Zeldovich,
Exactly.
not Weinstein.
Yeah, exactly. But
Which
it
I
seems
will
to
show.
conflict. It seems to conflict the Boyle theory, and it of course doesn't. So maybe you should clarify that.
We will come back to a point where a dynamo is in conflict with the Pontian gold theory. I will tell about this tomorrow.
And how to get rid of this conflict.
But I think a fast dynamo is defined by the fact that some limit of growth rate times a properly defined time is unequal to zero. It is limited. Here I have assumed from the very beginning I have an infinitely conducting medium.
Any other questions?
So, just a comment that at least figured out how to do that. I mean, I didn't really know this gradient, adding gradient of thing to the current doesn't change anything.
Yeah.
You can do it without a gauge.
Yeah.
Just take, what is it, Maxwell equation of the Ampere's law and take its curl. And then you will get del square of B is curl of J. So you can, so you need the boundary condition that D goes to zero at infinity to invert the curl. And then that's the result. I was a bit puzzled.
This is what Kant said, of course, to all these integrals to converge, we are somewhere integrals. You need the same boundary condition.
You had a question?
Oh yeah, so you talk about self-excited dynamo. This doesn't violate the Lenz theorem. So you have the magnetic field, and well, you have a current that creates a magnetic field, and then the magnetic field creates a current that decreases the magnetic field. But in this case, it looks like that is increasing instead of decreasing the magnetic field.
Currents are increasing when you have a dynamo. And the magnetic field and the currents are then both increasing.
So, but there is no, as far as I remember, there is a theorem in electrodynamics called Lenz theorem.
Oh, Lenz.
That's the opposite. That
Oh.
it should.
Okay.
It should. So where is the?
But the difference is here you have an energy supply through the motions.
Oh, okay. So you are providing
Yes.
this motion and
Yes.
getting.
That's work done against the Lorentz force. I think you said this.
Yeah.
Yeah. So it's not just a decay problem. You have energy supply.
Yeah.
It's a conversion from one energy form into another.
No.
Yes.
Yeah. Look at this. You have always, if you have finite conductivity, you have. Thank you. You have a dissipation of energy here by ohmic losses. We exclude this. But you can have energy from working against the Lorentz forces. You have Lorentz force and you move your medium, your fluid, against the Lorentz forces. you use energy for it. You have to do work, and this enlarges the magnetic energy.
Okay. We have, of course, the opportunity to talk to Karl-Heinz and the other lecturers during the group sessions tomorrow afternoon. So please spare any extra questions that you have for tomorrow afternoon. One more remark. You may have heard the grumbling in the background here. That's one of the regular dynamite explosions that they have here. They are building a network of highways down underneath, and in order to alleviate the traffic in some 5 years' time. So that's the reason why you may hear these explosions, and maybe 3 times a day maximum. Okay, there's thanks to Karl-Heinz again, and now we have a word from our Vice Director of NAVITA, Professor Radler. Please.
I did lecture this morning, so I couldn't do it first thing. But anyway, you are. I'm happy to see that all of you are here, or at least many are here. This is activity at NAVITA, which we have started and are pursuing, is to have summer schools and winter schools in different subjects. Last year we had a summer school in cosmology, and now thanks to the efforts of in particular Axel, we've got this winter school in dynamos. And we will pursue this kind of programs in the future. It takes a lot of effort that should not be underestimated by those organizing it. So, from my point of view, great thanks to Axel, and you're most welcome.
Thank you.